Okay. Howdy, everybody. Let's get started. Before I get into this, let me see which areas I should go into detail in. How many people here are currently running a database on Amazon Web Services? A few people. How many people are running a database on another public cloud? Okay. So it's kind of in between. Well, I'll go into a little bit of this and that sort of thing. So what this presentation is about is that because I decided that I had too much free time, I met up with some guys, one guy in particular in New Zealand at LinuxConf Australia, and we kicked off this project to start benchmarking Postgres on the various public clouds and different hosting options for Postgres. We've just started producing benchmarks for this. There's the URL for that, and you'll see that URL again. There's going to be a lot of work done in the future on it. I'll put the slides up later. And by the way, that guy, Ruben Rubio Ray, from managercloud.com, they are just launching now in the near future. It's a company that makes software to give you a single API for multiple public clouds. And as a result, we're actually testing out their API by doing these benchmarks. I also want to actually give some thanks to Heroku and Amazon Web Services for working with me when I started seeing benchmark results that were a little unusual, either to explain them or in some cases to fix problems on their individual clouds, and to provide me with some credit for running lots and lots of test runs on stuff. So before I get started with the benchmarks and other things, I want to talk a little bit about public clouds in general and AWS in particular. Because when you start looking at clouds from a performance perspective, you actually have to start spending more time thinking about them. Unfortunately, a lot of people seem to think that cloud hosting is somehow magic and is somehow qualitatively different from any other kind of hosting ever, and that you can get something for nothing. AWS and all public clouds are really just a bunch of servers. They're a bunch of servers with a couple to several layers of virtualization on top, shared storage, and an API. That's your definition of a public cloud. Now, the Amazon API is really full-featured, and it has a whole ton of nifty stuff, which is the main reason to use AWS in the first place, is the whole ton of nifty stuff. But that's what you're getting, is you're not getting anything that you couldn't theoretically do yourself. You're paying someone else to do it for you. And therefore, when you're looking at performance, you want to compare it to what would it be like to do this myself. So the good things about AWS, from my perspective, as somebody who does a lot of deployments for clients and helps clients with different hosting options and that sort of thing, fast deployment, obviously, new servers in minutes as opposed to months. Waiting for Supermicro or somebody to ship something to you. For a database, that means easy scale out by being able to add new read-only replicas as your load grows. And one of the big incentives for a lot of people, particularly in Silicon Valley where I work, is to minimize the number of ops staff that you have, because there's a huge shortage of available ops staff on the job market. And for that reason, everybody wants to minimize the ops staff by paying cloud companies to be the ops staff for you. Of course, the cloud company's hiring of the ops staff is the whole reason why we have the shortage in the first place. So it's a lovely little case of very profitable bootstrap levitation. And the really good thing is, at the low end, if your needs are fairly low end or limited, or at least low end or limited right now, hosting stuff through public clouds is usually very cheap compared to your other options. Unfortunately, it doesn't tend to stay cheap as your needs grow. As your needs grow in comparison to, say, having your own hardware, putting stuff in the public cloud starts becoming more and more expensive comparatively. And, you know, once again, a great business model, right? The first one is free or very cheap, right? And it's the ones after that that cost you a lot of money. The other bad things are, compared to running your own hardware and OSs and even virtual OSs, system resources are actually relatively poor. You know, as in, you know, if I'm buying an actual, you know, 2U rack unit, I can easily get it with a 1/4 terabyte of RAM these days. That's not that expensive anymore. But it's a 1/4 terabyte of RAM is like $3,000 a month on AWS. So the minute that you get out of this very small, limited virtual server, it becomes really expensive. So this is one of the bad things. Another bad thing is that being on a virtualized platform where your interface into it is an API and you have no control over the physical plant at all opens up a whole new set of security vectors for people to break into your stuff on, as some people have found out the hard way. This was a company called CodeSpaces. They failed to protect their AWS credentials sufficiently. Somebody got into their AWS console, decided to hold their business for ransom. They refused to pay, and they no longer exist, actually. He deleted everything, including the backups, because the backups were all in AWS. So, but the really ugly part about being in a public cloud is that everything is shared, right? Network is shared, I/O and storage is shared, CPU is kind of shared. I mean, theoretically, you have dedicated CPUs. In reality, there's a lot of sort of burstiness in there. And what this means materially is that your real performance depends on somebody else's peak load. Or, to put it another way, sharing is not caring. The final thing you have to be cautious about when hosting things on the cloud, particularly things like transactional databases where you have stateful information which is valuable, is that cloud instances are ephemeral, right? Something goes wrong, there's a software error, somebody sends the wrong command, somebody clicks in the wrong place on the graphical, you know, website, or just, you know, the cloud host needs to rebalance their workload, et cetera. Those instances can and do go away. And for that reason, doing serious disaster recovery, which is maybe something on your own hardware that you can wait until you're up and running to do, is something that you need to do from the first, you know, hour of deployment on any kind of a public cloud, because you have to expect those database instances to disappear, to be unreliable. You want to have, it's not replicas or backup, you really want to have replicas and backup in order to cover the various kinds of failures. So one of the other questions is, if, okay, what we're looking for is to test various cloud services. Why use Postgres for this test, as opposed to like Sysbench, for example? And the reason for that is that one of the things about transactional databases is that they actually give a pretty good whole system workout. Us folks in the database industry are very heavily into how can we maximize our usage of all of the resources on the system simultaneously. That's what we do. We spend a lot of time thinking and arguing on mailing lists and writing code to make sure that every megabyte of RAM and every percent utilization of every CPU and every gigabyte of bandwidth on the storage is in use at the same time, because as far as we're concerned, if it's not, we've left performance on the table that we could have been using to deliver data faster. So for that reason, I find transactional databases are sort of a better test of the kind of whole performance experience than other kinds of benchmarks that only test one system at a time, as opposed to testing them all at once. So for our shootout, we have a cast of 3 characters here. We have the Gunslinger, our roll your own EC2 option, the Rancher, which is RDS, and the Dandy, which is Heroku. So The Gunslinger. Right. Low cost, rough, gruff. Doesn't bathe very often. This is our EC2 option. This was originally obviously the only option for posting Postgres on AWS, which is, set up an EC2 instance, install, roll your own. Really simple. Create an EC2 instance, configure PostgreSQL on it using the packages of your choice, and configure PostgreSQL yourself. The advantages of this, as you'll see when I do price comparisons, it's the cheapest option, obviously. It's highly configurable. Anything you want to do with Postgres, you want to run a Postgres fork, you want to install whatever extensions you want to run PostgreSQL, you want to run multiple Postgres as one virtual server or whatever, you can do whatever you want because it's your instance and you're paying for the OS and not for the database. The drawbacks are, from an ops perspective, you really haven't, the only thing you've saved yourself is hardware wrangling. Everything else you still have to do, backups, installation, updates, OS updates, all of these things are still your job, or you still need to hire ops staff to do them. And you pretty much have to configure Postgres for any real workload because nobody's helping you configure it for you. Now, you can do lots of other stuff. One of the great things I love about running on AWS is that I use the AMI Amazon Machine Image facility all the time in order to create images that become my template for particular database services, and for that matter, as a way to spin up replicas, depending on the size of the database. And you have access to all of these other services within the AWS thing. They have, the Elasticache thing and some of the queuing stuff. I'm actually, playing around with Elastic Beanstalk and Docker for deployment and that sort of thing, S3 storage for backups, and you've got all these different services. AWS has a wide array of instance types. In these, the primary ones that you're going to use, tend to use 3 different ones for databases. Use the general purpose ones for just about anything. For basically, if you don't really know what you're doing and you're just setting up your first Amazon instance, one of the M class, which are the general purpose ones, is good. For a lot of databases, as sort of a cost break thing, we end up using the R series, which are designed to give you the maximum amount of memory. Because with AWS, and I'll read this again, it becomes really critical to try to keep your entire database cached in memory. And so you want a little bit more RAM. But if you can't keep it cached in memory, they've got this I series which come with very large instance SSDs, which is an option for doing analytical databases. One of the things about public clouds is that all of your storage is generally shared, network connected, and virtualized, which means that the cost of an individual synchronous write and the response is much higher, and the response time is much longer than it would be on own hardware, as in like an order of magnitude longer. And for that reason, it becomes really critical not to be routinely reading individual blocks of the database off disk if you can avoid doing so. So like if you have the choice between an M3 instance that has 64, within your budget, gigabytes of RAM and could cache 80% of the database, and an R3 instance that has 100 gigabytes of RAM and could cache 100% of the database, go with the R instance. Makes a huge difference. The other thing that you have to think about now, because Amazon has given you a whole bunch of different storage options, and this is not something that you see so much on the other clouds, are the different storage types. So your sort of standard for databases is to use their elastic block storage with this provisioned IOPS option. This has the advantage that Amazon makes some guarantees about the amount of throughput and response time that you're going to see out of that. So you basically get it in, what they call IOPS, what Amazon's definition of IOPS, so 1,000 writes per second or whatever depending on, and you pay different rates. It is a disadvantage that it's expensive. Often you'll pay more for the provisioned IOPS storage than you will for the instance that's using it. Now, you can use this general SSD option that they have for storage. The drawback to the general SSD option is that, well, the advantage is it's actually better for bursts. I did some early benchmarking and that sort of thing, and we were seeing results that were about 20% better. But the problem is it's not better for sustained stuff, and the variability in response time from the storage is much, much higher than it is for the provisioned IOPS. You can go with another option, which is instance storage local SSD. A lot of the new instances have local SSD that, because it is local to the blade or at least the rack for the machine, does tend to be a whole lot faster. The problem is that if your instance restarts unexpectedly or the underlying machine restarts unexpectedly, the data doesn't necessarily come back intact. We think that they're using some kind of hardware caching on it that's not necessarily restart safe. So this can be an option if you really need the performance, but you need to look at having extra levels of redundancy, and redundancy that'll be safe against having an instance come back up, maybe restart replication but be sending corrupted data. That being said, we've had to go to instance storage for SSD for some of the analytical workloads because even with the provisioned IOPS, it was just too slow otherwise. How much in the case of the analytical workloads that I was working on, it was, well, we got like double the real throughput. I haven't really tested with pgbench for this because I had too many other tests to run, as you'll see. I will be doing that later on. One of the things to keep in mind here is that a lot of people go this provisioned IOPS and they think of this as comparable to the IOPS rating that you would get on local storage. Like, so like, hey, I've got, 3,000 IOPS on this Hitachi SSD that I just stuck into my local machine. The thing is, Amazon's IOP is not a disk manufacturer's IOP. First of all, it's a limit. Amazon's not guaranteeing you at least 1,000 IOPS. It is guaranteeing you exactly 1,000 IOPS. I'm very impressed with their level of engineering into I/O controlling, in that if you've asked for 1,000 IOPS, you will constantly, like, if you do something that just like do the Postgres fsync test, you'll discover that it will on a constant rate be between 950 and 1,050. So you're never going to get substantially over that 1,000 unless you pay for the extra. Also, the other thing is that an IOP is limited to 8K. It doesn't get any bigger than that, two Linux pages, disk pages, which means that effectively it's one Postgres page lookup, which means that if you get into something like a nested loop over an index that's doing random lookups in a table, your PRIOPS rate becomes the number of rows per second you can read. And 1,000 rows per second is not actually that fast. So something to keep in mind when you're actually looking at this in terms of storage performance for a database. Other things you need to set up, I set up WAL-E to S3, set up replication, which is really into another availability zone, monitoring for instance failure. SSL is not really optional in a public cloud. You're sharing that network, and other things. Got a few configuration tips here for things that are not, necessarily something that would be critical on regular Postgres stuff, but buffers for the transaction log, set the random page class down as you would for SSD storage in general. Stats temp directory, because of storage latency, if you're on elastic block storage, having the stats write to a RAM drive for its cache instead of to disk becomes a real performance boost on workloads. And synchronous commit equals off, which is actually tends not to be that much of a benefit on own hardware, which is basically you tell Postgres not to synchronously write to the transaction log, but rather to write in batches, which means that if you have an unexpected shutdown, you'll lose like 200 to 400 milliseconds worth of data. Can be a big boost on a public cloud, and on AWS. For this benchmark, we decided to test two different sizes. We wanted to look at a small size, our junior gunslinger here. This is sort of your economical option. This is somebody who's looking for a low-cost hosting option for Postgres. So in this case, for Amazon, we're using an M3 Medium. It's got 1 core, almost 4 gigabytes of RAM, and we've given it a 40 gigabyte, 1,000 PRIOPS share for that. We also set up a larger instance. This is sort of your performance instance. It's actually kind of a mid-level performance instance. We do have a limited budget for doing this testing. We wouldn't mind testing a very large something on the high end, but we can't afford to do the number of runs that we would like to do with that. So this is sort of mid, 8 cores, 60 gigabytes of RAM, 4,000 PRIOPS set up for writing that for Postgres. So let's do actually a little bit of cost breakdown. Amazon makes it a little cryptic if you don't understand the pricing on how to do this. So for the junior gunslinger, for the small instance, that's actually really quite cheap, $36.50 a month. As you can see, we pay more for the storage than we do for the instance. And that would be a reason where if actually response times are not critical, you might actually use general SSD because it's substantially cheaper. Need to have the archive for backups. We're going to have a replica, which means we've got to have 2 of these at least. And then, like the cell phone companies, with Amazon, plus you have your miscellaneous charges, which are really hard to predict. Network transfer, bandwidth, some of the other services, API overuse, a whole bunch of other random things that Amazon puts in your bill, just like the phone company does. So I'm estimating those actually in the future charts at about 40-something bucks a month. It can be much higher than that if you're pulling data in and out of AWS as a warning. You can do this a little bit cheaper. That is, if you don't really care about failover, you just care about not losing data, you can just do the continuous backup to S3, not have a replica, and obviously save yourself some money, but this does mean that if you lose that master instance, you're going to be down for however long it takes you to restore to a new instance from S3, which will be some number of hours. For the bigger instance, it's going to be a little bit, actually a lot more expensive. So again, adding up some sort of the same cost breakdown, we're looking at like $750 a month or $1,500 a month for one with a replica. So let's look at RDS. This is kind of our middle option between roll your own and Heroku, between the Gunslinger and the Dandy. First, go to the AWS RDS, choose PostgreSQL, select instance size and storage, launch, and you then connect and do all of your stuff over port 5432 and via the Amazon API if you want to change anything about the instance like configuration. Advantage of this over to EC2 is simpler deployment. You're not writing a bunch of Puppet or Chef scripts in order to set up the configuration everywhere that you want to. They manage updates. They manage monitoring for uptime. You can create replicas relatively easily because they got a little thing through the Amazon API now for spinning up read-only replicas. And they provide you with two different redundancy options. One is this thing they call multi-zone, multi-availability zone redundancy, or you can have replicas. And they also give you a nice API interface for snapshots for the database. Some of our drawbacks here, though, are You're limited in which Postgres extensions you can load to the ones that they've pre-cleared. And it doesn't include certain popular ones like PL/Python because they can't figure out how to secure it so that you can't get out of that sandbox they placed you in. It's 9.3 only, and they're also not very speedy at applying the community updates. Like right now, it's still 9.3.5 and not 9.3.6. Don't have any shell access. Might or might not be a problem depending on how you're there. And you still might have to actually get in and modify the Postgres configuration. They do a little bit of auto configuration, but it's not anything, on the way of active monitoring or a lot of smarts. It's just they've applied some of the same rules of thumb that all of us use for initial new instances. You can obviously integrate into all of the AWS stuff you'd integrate in otherwise. You have a variety of options and hosting sizes. Oh, actually, I needed to update that because they've got the i3 instances now available. Those weren't available earlier on. Again, you really want to get enough RAM, and you don't have the full set of storage options here. It is all EBS, and your only choice is PRIOPS or not, or how much PRIOPS, the provisioned IOPS. Now, the redundancy is a little bit complicated here because here's the thing. Amazon has its own replication thing that it uses for multi-availability zone stuff. And that is their high availability offering where they guarantee automated failover if the first instance stops responding, et cetera. But that doesn't use Postgres replication. That uses their own proprietary thing, which is much slower than Postgres replication, which you'll see when I actually get some of the performance figures back. Or you can use Postgres replication, but then Amazon doesn't do any of the automated failover or monitoring things. You have to do that on your own via the API or whatever. And obviously you want to have setting up database snapshots. An important thing to know with this, by the way, if you delete the RDS instance, any automatic snapshots from that also get automatically deleted, which I think is a bit of a misfeature, but that's how they've set it up. So it's more or less the same as you roll your own. Don't start out by changing the configuration except for things that you know you need because the defaults are more or less okay by default things. Obviously, there's fewer security options for this. You've got no access control list except whatever you set up through the Amazon firewall. So here's some of our cost breakdowns here. So for single option, redundant option, large single, large redundant option, you notice that we've taken a significant step up in cost here. Yeah?
For all the kind of mishaps that RDS seems to have, are they road mapping that? Like, for instance, the failover, when there's like a minute gap in failover, so on and so forth. Are these things road mapped to actually make this like a viable service?
Okay, I didn't actually, I haven't heard of the minute gap failover being a problem before, actually. So I don't know the answer to that. Because replication for Postgres only became available in December, for our client customer base, we only have a few customers who are on RDS and any kind of HA option or whatever, and none of them have had to do an automated failover. So it'd be something to ask Grant about. So let's talk lastly about our dandy here, our white glove service option, which is Heroku. The idea is log into postgres.heroku.com, choose create database, pick a size, launch, connect. That's it. The advantage of this is that this is really the option of I want someone else to manage everything. Really, or I have no ops staff and therefore I need someone else to manage everything. They have some of their own special Heroku-only features, accessories for Postgres, and plus they have all the latest community stuff. Well, not all of the extensions, but they have a lot of the latest community stuff, including sometimes features of things that are not officially production releases yet, like new Postgres betas. Drawbacks, you can't configure it at all. They configure it for you. They kind of assume that you are running like a Rails or Django or Node app, and that's your use case. You don't have any control or insight into, for example, even what availability zone they're in. You know they're in US East, but not other than that, which means that if you're running other services that are outside of Heroku, it can be hard to put stuff into the same availability zone. Again, limited extensions and versions, and no shell. Now, I did mention that they have a few Heroku-only things. This includes if you're heavily into a Git commit-based workflow, you can use that to manage your databases now, too. Some people really like that. Not so much my thing. Data clips are sort of like materialized views for the web. And you do this whole follower thing, which is, again, their very user-friendly replication management interface. Plus a bunch of other things. Actually, both RDS and Heroku now offer automated disk encryption options for their stuff, probably because of government requests. But this is actually kind of the big feature of Heroku, which was when I set up the large instance, 24 hours later, I got an email from a Heroku technician asking if they can help me optimize my instance at all. This is not something that you will get from Amazon RDS or any other public cloud I know of, frankly. So your choices are 5 database sizes, 3 levels of HA/uptime, and that's it. So 15 options, basically. That's your menu. The 2 that we actually used, we used a small standard 2, which is equivalent in resources to an M3 medium, although it's implemented differently. And a large, which is a standard 6, which is actually just on an R3 double extra large Amazon instance. It's important to know, and you'll see the effect of it in some of the scores later on, that the standard 2 is actually a multi-instance larger Amazon host that is shared with several other people running small Heroku instances. Pricing for this is pretty straightforward. They have menu of prices, $200 a month if you're just going to use archives for redundancy. If you actually want high availability to a replica, then it's going to be $350 or $3,500 for the large size. Again, you can see all cloud hosting. The small ones are cheap. The large ones are much less cheap. The one nice thing about this is that's it. That's all you pay. There's no miscellaneous charges, which is a nice thing when you're planning. So let's do our shootout. So you've seen all the prep and that sort of thing. So time for a shootout. So the initial tool we use for the shootout is pgbench, which is a micro benchmark that ships with Postgres. The reason why we've used it for our initial tests is that it's very fast to set up and run. And we're doing automated deployment of benchmark tests to multiple clouds and doing a lot of runs. So it's very fast to set up and run. It has some really strong drawbacks, though. It doesn't do any complex queries. It does pretty much pure random data and access. And the result of that is that it actually turns out that tuning almost doesn't matter, at least in terms of like doing Postgres.conf tuning and that sort of thing. Almost doesn't matter because it turns out that if you're just selecting random individual rows and updating random individual rows, very few of the settings that you can change have any effect on that workload. So like when we were doing the initial tests, we were doing separate scores for a configured EC2 instance versus an unconfigured EC2 instance. We actually stopped doing that because the scores were so similar. It's also a little bit of an unrealistic balance of work because it's either it's just read-only or everything is a read-write. We're looking for future better benchmarks. But we did do this in 3 different sizes in order to get an idea of what different workloads would look like. So first we did a database that would fit in memory, approximately 30 to 50% of RAM. So a little bit bigger than Postgres' dedicated cache, but not big enough to use up all the RAM, and with write transactions. And then we did that same size database with read-only queries. And then we did a database that was 150 to 200% the size of RAM, so that we would force the instance to do swapping on and off of disk for that workload, and again for a read-write workload. And the idea was to see how these instances, perform differently, particularly because Heroku had really stressed that they had optimized for the read-only workload. I don't need to go over this in general. For people looking at my slides later, you can also look at the project. These are the actual pgbench settings that we used for this. 4 threads for the small ones, 16 threads for the large ones, different sizes. So out of this, we pulled 2 metrics out of these tests. One is transactions per second, which is how many, in the case of the read-write test, how many transactions, and that actually does 1 read and 2 writes, I believe, in those. And for the read-only, it's just a straight read query. So how many read queries per second? And then the other thing that we actually did metrics on was load time, because pgbench starts out by inserting a few thousand or a few million rows into the database. And one of the things that people do a lot on databases is actually doing loads or collecting data. So we thought that would be actually good to see how that did on the different databases, particularly as a measure of I/O performance, and it'll get more interesting when we get into other public clouds. And then we have to run everything a whole lot of times. The reason we have to run everything a whole lot of times is that we discovered that there's a huge amount of variability. As a matter of fact, one thing I got out of doing this set of benchmarks is for our clients who are on AWS, we're going to start benchmarking their instances and deleting and redeploying instances until we get one that shows up better. Let me actually show you what I mean in a box plot. Well, not that kind of box plot, this kind of box plot. And by the way, anytime you can be doing statistical analysis, anytime you're doing like that, benchmarking, whatever, if you're not doing a few box plots, you're probably doing something wrong. Because you really need to actually see this. Because, for example, this is the large in-memory read-write test results. And if you look at the amount of variability we have here between the different test runs, it is huge. So this is where it aligns in the set of different results. So like our median is 1685 read-write transactions per second. But if you see, let's actually give you multiples here. The maximum is up to 4 times the median, and the minimum is as little as 1/3 of the median. So you've actually got an almost 10x variability between the fastest and slowest runs, which means, yes, you can get bad instances, and that's something you need to be testing for anything you're going to run in production, because otherwise you'll go into production with that bad instance and you won't understand why everything sucks. So now time for a whole lot of graphs. I hope you're ready. So just throwing this in as a feature grid, because you should see that there actually are some feature differences among this. One of the notable differences is versions. I mean, obviously EC2, you can do anything you want. RDS is 9.3 only. Heroku is 9.3, 9.4. We'll do the betas when they're available. There's a bunch of other, sort of qualitative different things. I don't really want to go over this in detail. More here to talk about the performance. I'm actually going to put up the pricing I showed you earlier because it was on different slides and you really have a chance to compare it. So this is the small instance pricing. And you notice in the small instance pricing, it's all pretty similar. EC2 is a little cheaper than RDS and Heroku, which are pretty much about the same price. Large instance pricing is a lot more different. We've actually got kind of a straight vertical graph. However, I actually need to introduce another factor there, which is that there's a real difference in how much ops time you need for these different options. As a matter of fact, one of the things that we actually do in our company, one of our ways of making money, is that we do this cloud DBA thing, which is a remote DBA for people who are hosted on public clouds or other virtual forms of hosting. And this is a maintenance contract for one of our database geeks to keep track of your virtual server and make sure that everything's running okay, and help you with deployment requests and a bunch of other things. And so we do people who are hosted on these different options. And we find that somebody who's on EC2 for like an individual server probably uses about $1,500 a month of our time. Somebody who's on RDS uses about half as much, and that's because we're not really dealing with backups and that sort of thing. And Heroku has been a terrible business partner for us. As a matter of fact, the only thing we end up helping anybody with on Heroku is periodic slow query troubleshooting. That's pretty much it. Certainly zero for maintenance. So if you factor that in, then the graph starts looking a little bit different. Heroku is still a little bit more expensive, but only a little bit. So now let's actually go to performance here. So let's look at load time first. So this is loading the small instance for the in-memory database, about 2 gigabytes of data. Obviously, a lot of this is determined by, this is going to work out our network I/O and transaction log and disk I/O. We've got the blue is the median, the red is the 90%, and that says in 90% of runs will load in this time or less. And higher is slower, because this is the number of minutes that it took to load. And so you can see here that we have a real problem with load time on the RDS small instances, comparatively speaking. I actually contacted the Amazon RDS crew about this, and they basically said that it's because of a lot of the stuff that they do for their redundancy, which is not possible to turn off or optionally. And this is where you really see the difference with Heroku. You see a couple of differences. One is, with Heroku using Postgres replication as opposed to using their own archiving stuff for redundancy. By the way, the reason why we actually have two options here for RDS is that first option is RDS using either as a single node or using Postgres replication for redundancy, but without any of Amazon's multi-AZ, failover stuff. The second one is a multi-AZ instance with automated failover. And the reason why RDS gets two columns is that you'll see in some of the later tests the performance is substantially different. So now here is loading an on-disk database. That is a database that is, I think it was about 6.5 gigabytes for 3.75 gigabytes of RAM. And again, we've got our own EC2 instance, we've got Heroku and that sort of thing. So one of the things we're actually going to see here with the small Heroku instance is you think, why is the small Heroku instance faster to load and faster in some other things than doing my own on EC2? I'm pretty good at tuning EC2 servers. And the answer is because this is actually shared between, the virtual machine is shared with a lot of other tenants. And I'm being a bad neighbor. I'm actually stealing their resources by running a heavily bursty workload. But that does tell you that the Heroku shared, the small instances can be a real benefit to you if you have a workload that is bursty in nature. Whether or not Heroku will clamp down on your usage if you've been doing this for a couple of months, I don't know. So loading the large nodes becomes a little bit different. So this is loading an in-memory database about 15, 16 gigabytes on a larger node. And here we see actually that my EC2 tuning experience pays off a little bit in getting a little bit faster load time. Heroku and single node RDS being about equal, and then RDS HA being substantially slower. This is why, and this is because of Amazon doing their own DRBD-based replication to the other availability zone. This is loading the large database. So here we're loading 100 gigabytes of data. Again, you can see EC2. The Heroku is a little bit slower than single node RDS. I'm not quite sure why. We did go over it. Wouldn't really know why the difference there. I'm guessing, and we'll see this in some of the later read-write tests, that if you sign up with Amazon RDS, the storage that they're giving you is somehow different or maybe closer in a network sense than if you just do EBS provisioned IOPS on your own. So first benchmark, the in-memory read-write test. A taller is faster here. This is transaction. And again, here we've got blue is the median result. Red is the 90%, as in 90% got this TPS or higher. So here you see our ability to be a bad neighbor on the shared Heroku instance being a huge benefit to us. because we're getting vastly higher TPSs on Heroku than we are even on our own EC2 instance. And that RDS is actually able to perform more or less like a hand-configured EC2 instance, except unless you're using multi-AZ. So same thing this time on the large node. So this is a much larger dedicated node and this sort of thing. And now you see we don't have the ability to take advantage of overshared resources on Heroku, and so performance drops to be more or less equal with RDS, a little bit slower, and I think that's actually the storage issues. And for the EC2 test, we're actually much slower on this in-memory there. And I'm actually going to be revisiting, particularly, we got a lot of variability on that one in terms of storage performance, even though we had provisioned IOPS. And we're really kind of paying the penalty for that because I had some very high scores in this one, but also had some really low ones. That was the one, by the way, I showed you with the box plot. And there you're seeing the result of that level of variability. So in-memory read-only test. And you know, again, this is the small node, and this is what Heroku really prides themselves on. So certainly in the bursts for the median, although you see a kind of steep fall off as you try to get to the 90% response times. Now, this is another weird thing that I don't have an explanation for yet, because this is across like 7 test runs. And there's no particular reason why multi-availability zone RDS should be faster on a read-only test. I'm kind of wondering if it was just instance luck. I mean, there are several incarnations of instances here, because Amazon doesn't load balance to the failover instance. So I don't have an explanation for that yet. Here's the read-only test in the large node. And here's more what I would have expected to see out of the RDS. Well, actually, I wouldn't expect the RDS HA to be any different for this. And so I really don't have explanations for why the high availability version of RDS is performing so differently on a read-only test. You know, and for the rest of this, EC2 Heroku RDS is looking about the same. And by the way, this is very different from when I first started dealing with Postgres and AWS. When I first started dealing with Postgres and AWS, we were lucky to get 1,000 queries a second off of an AWS instance. You can't really see the numbers here if you're in the back, but that line right there is 25,000 queries per second. It's no longer the case that, oh, you can't go on a public cloud because the performance will kill you. It's a viable option for, you know, anybody except at the very high end. Now here's our on-disk read-write test. So this is a 100 gigabyte database on an instance with 60 gigabytes of RAM. And here we're seeing the real effects of read-write. It's interesting that now here we see, because I know more about tuning Postgres for better disk access, this is the one time that we actually see a real difference from hand tuning compared to RDS or whatever. Heroku actually had some nice bursts, but again, if you hit the 90% response time, not as good. And a lot of that has to do with how Heroku allocates a lower level of provisioned IOPS than I would allocate for an EC2 of the same size. This is the same on a large node. So actually that was the small node, sorry. And this is the same on the large node. So now, before I take questions, let me tell you a little bit about what's next for this project. Obviously, we're going to be testing this in other clouds. I actually have our first, 3 rounds of results back from Rackspace and DigitalOcean. I just haven't had time to compile them, and importantly, I haven't had time to understand Rackspace and DigitalOcean's pricing models, so that I can actually do a cost comparison, which is kind of critical, particularly because we can't actually allocate instances of the exact same sizes. Like the smallest instance on Rackspace has 4 cores. So we have to do a cost comparison and not just in a performance comparison. And we're also going to be doing OpenShift because they've got a Postgres thing and Google Compute Engine. maybe Microsoft Azure's Postgres thing to get a good comparison across the cloud stuff. We also need some better benchmarks. I mentioned the limitations of pgbench with its whole sort of random access pattern. We'd really like to get away from that. My problem is that I'm looking for a better benchmark that presents a more realistic workload, but is fast to start up and tear down. And we haven't found that benchmark yet. Here were a bunch of ideas. I also kind of want to do a NoSQL-ish benchmark, something with Postgres, JSON-B, et cetera, that then people could run against the NoSQL data store of their choice to see how that works. We also need some much better visualizations, and particularly if anybody is into that. I was originally trying to do a bunch of stuff in Python for the matplotlib for the graphs and that sort of thing. Having a lot of trouble with it, I ended up just producing all those graphs on calc because I couldn't get them to come out the way that I wanted. And I actually want to do more interesting comparison, multidimensional comparison graphs, and I could really use some help with that. Also, ran out of time for this. If anybody who follows my blog, Database Soup, will have seen the running with scissors configuration. This is if you're running Postgres in the public cloud and you don't care about your data, how fast can you go? There are circumstances where you'd want to do that. For example, it may be a replica that is never going to be failover replica and therefore disposable. And I did do a bunch of tests for that, but the numbers look wrong, and so I didn't want to present them here because I think there's something wrong with the way that I configured it, and I want to rerun that. How did you do the no transaction log? Or is that just fsync off? Yeah, it's fsync off and that sort of thing, and I'm also, one of the other things I'm experimenting with is actually literally putting the transaction log on a RAM disk to see if that makes a difference, and so that's actually why I need to do more runs to figure out the numbers for this. Yeah. Okay. Well, so if we're going to do questions here, why don't you take the mic because they are recording the session. Oh, okay. And that way you actually get picked up on the recording. So go ahead.
I was just saying it'd be interesting to do a hack of Postgres where we just don't write transaction log at all.
Yeah, actually, that's not the big problem with Postgres in ephemeral mode. The big problem is that we can't turn off checkpoints, which is a much bigger I/O load. Turns out writing completely asynchronously the transaction log if all of your tables are unlogged, well, that doesn't work if you have a replica, though. Right. But there's ways to get around the transaction log thing. There's not a way to get around checkpoints. And if we're not writing the transaction log synchronously, then we shouldn't really care about checkpoints, but there's no way to disable them. More questions?
Have you looked at the sysbench OLTP as an alternative benchmarking framework for this?
Yeah, I found the sysbench to be really too heavy on CPU in terms of what parts of the systems that it works. And overall not a huge improvement over pgbench, which I already know how to automate. I'm really looking for something. For example, I'm looking for something that might have unevenly distributed data and be doing a variable workload of transactions. So not just the same transaction repeatedly. More questions? See, there's one over here.
Would you mind sharing some of your initial results for DigitalOcean?
Yeah, let me see. Oh, by the way, so this is a bunch of, pulling up some of the CSVs of all of our test runs, to give you an idea. So you can actually go to the project.
So all the raw data is available in Git?
Yep.
Public Git?
Yeah. So like, for example, this is the DigitalOcean small instance. And getting a pretty good performance there. I told you I hadn't compiled these at all. So that's just one run, but 868 is actually higher than anything we saw in the AWS small instance. So I'm curious what it looks like on a large instance. Actually, large instance performance is pretty good too. That's not higher than we've seen on some of the large instances of Amazon, but it is higher than the median. Load times are about the same, which means it's probably being limited by network speed. Yeah, so that's all if you go into the data directory on the Git repo, and you will see we're continuing to do runs, so there'll be a lot more test runs appearing there soon. Other questions? Hold on, let me get you the mic.
For Amazon, what availability zones did you run? What data centers for Amazon?
Yeah, so mostly we did our test runs in US East because that's where Heroku is located, most of Heroku's stuff, and we're trying to keep it comparable. I did do a bunch of test runs in US West because that's where I host my stuff most of the time in order to see US West South, so California, because that's where I host a lot of my stuff. And I did actually find that we got better instances more often in US West.
Yeah, that's, I think Oregon is actually probably the best right now.
Which one?
Oregon.
Yeah, I believe it. And again, that's part of it. And one of the things I'm going to have to caution when we do the other, the tests of the other clouds, like part of it is I think we're seeing much better performance numbers out of like Rackspace and Google because compared to Amazon, their clouds are currently underutilized. So particularly in the storage, you get the advantage of having hardware that was built out with the plan of having more tenants, and as they populate their clouds, performance will get worse, the same way that it did on Amazon in the early days. Yeah, so I agree with you. I haven't done test runs in Oregon. More questions? Oh, wait, one right here.
Would you apply your read-only, your running with scissors configuration to read-only replicas?
Yes, if you never plan to fail over to them.
Right.
And don't plan to cascade from them. So, yeah, there'd be reasons to do that. The question is, if you're just going to be running read-only stuff on that replica, how much faster will it be? And so I will have an answer to that question in my blog next week. One more?
Couldn't you still do streaming off of that even if a sync turned off? That's only for writing.
Yeah, I wouldn't do it. The reason why I wouldn't do streaming off of a replica that had been set up as ephemeral is that I wouldn't trust it not to have a corrupted write-ahead log, particularly if the instance, say, restarted.
Oh, right. Well, yeah, if it restarted, then.
Yeah.
Okay. I believe last December, Amazon got general SSD storage for the RDS instances.
Mm-hmm.
I guess I wonder if you actually tested it for the.
I didn't test it because I wasn't using it for the EC2 instances because of the high degree of variability. Like, you can actually get good benchmark performance out of that because of the burstiness of it. But that's not necessarily what you do in production, because a production database would obviously be running for days, weeks, months, years, and you want better constant performance rather than necessarily burst performance. The general SSD really is equivalent to somewhere around peak, 3,000 IOPS, et cetera. The problem is that goes up and down on constantly. So if you're trying to save some money and you don't really care about having consistent response times, then obviously it can be a good option. Or if the database server is only going to exist for a short time, I could definitely see using general SSD. But for a database server, virtual server that's going to keep running, I wouldn't.
Okay, thank you. And also, when you run the benchmarking testing, you run your tool in a EC2 instance, right?
Yeah.
So I guess you were, well, I wondered, you were considering that maybe the latency might vary between the EC2 instance and the RDS compared
Oh,
to...
we're pretty certain the latency varied, actually. But that's one of the things you have to test, right? Because the whole goal of the benchmark is to simulate some kind of an application, and the application is going to be located in a different instance. Even if they're in the same availability zone, the latency between the instance and the back end is going to vary, and that's just why you have to do a lot of test runs. But again, we're trying to benchmark things that would affect you in real life, and that is something that will affect you when you're in production, and therefore it needs to be part of the benchmark.
Yeah, I mentioned it because of the Heroku case, because...
Yes. Yeah, and that is an issue with the Heroku case in that when we're spinning up our Heroku instances, we don't know what availability zone they're going into. And we discussed this with the Heroku guys when we're running the benchmark, and they decided to just live with it. And part of that is because if you are spinning up on postgres.heroku.com and running your own application, you don't know what availability zone it's in, so you're going to have the same issue.
Oh, thank you very much, Josh.
Yep. You're welcome. Okay, well, thank you, everybody. Keep following either the project and or my blog, Database Soup. There will be more of this posted. I will be giving presentations at the Postgres conference in New York City and the Postgres conference in Ottawa with updates to this benchmarking project and more clouds and that sort of thing. And I'll put the results on my blog, and they'll be in the project as well, so you can follow along. Thanks.